In the last video, we were talking about total energy changes, and we said our total energy is equal to work plus heat. And then we had also said that we don't always have work, right? Our most common type of work in chemical systems are pressure, volume, or expansion work. It results from a volume change. If I don't have a volume change, right, if volume is constant, then work isn't occurring and my total energy change is due only to heat. I want to talk a little bit more about that heat in this chapter, and we're going to define a new term called our enthalpy. And then for us, what we're going to look at is our enthalpy change, right? We're looking at it from the point of view of our system. So is heat entering, right? Is enthalpy entering or losing my system, entering or leaving my system? My symbol for enthalpy is H. So enthalpy change is going to be delta H. And this is defined as the heat of the reaction. Now be really careful to not get delta H in Q. Q is heat transferred. And this is a really fine but important difference. So Q, we said, was heat transferred, right? Is heat entering the system or is heat leaving the system? My enthalpy change, or delta H, is the heat of the reaction. So it's specific to the amount of moles that I have in my balanced equation. It also depends on the physical states of my substances and then also temperature and pressure. So depends on the amount of reactants and products. Remember, our SI unit for amount was the number of moles, so it depends on the number of moles. Kind of a way to relate the two, if we were to take Q, my total heat transfer, divide it by the number of moles, we're actually going to get delta H. So Q is my total heat transfer. Delta H depends on the number of moles that I have. So my units for Q would be joules, right? My units for delta H would be joules per mole, often kilojoules and kilojoules per mole. So it depends on the amount of reactants and products. It also depends, I said this, but we didn't write it down, on the physical states. So is it a liquid? Is it a gas? Temperature, so T for temperature, and pressure. Because it depends on all of those things, we can actually define a standard state for thermodynamics. Be really careful. We had a standard states in gases, for gases also, right? In chapter 8, we defined STP. They are different values for thermodynamics than they were for gases, so just be really careful. So standard state for thermodynamics is 25 degrees Celsius, right? For gases, my standard state was 0 degrees Celsius, so be really careful. This is 298 Kelvin. And then the pressure is the same, so it would be 1 atmosphere of pressure. And then if it was a solution, it would be a 1 molar concentration. So just be careful. It's close, right? STP for gases, standard temperature and pressure, is 0 degrees Celsius in 1 atmosphere. Standard state for thermodynamics, 25 degrees Celsius, 1 atmosphere. And then if it's a solution, a 1 molar concentration. It is important because remember, we just got done saying that my enthalpy does depend on my temperature and pressure. And the way that we would indicate that they were at standard state is we use a not symbol. So if I write delta H and I put this symbol up here, this tells me that it's at standard state, that value was measured at these set of conditions. If you were to measure it at a different temperature, then the value is going to be different. So this indicates standard state. In 152, you'll actually have an equation relating standard state to non-standard state conditions. So indicate standard state conditions. So delta H delta H is my heat of reaction. That little knot symbol indicates that it's at standard state. If it's not at standard state, then temperature and pressure should be listed. It would be good form to always list that. The relationship between Q and delta H is that Q is my total heat transfer. Delta H, my enthalpy change, depends on the amount. So if I was to take Q divided by that amount, I get my enthalpy change. I do have an example for us. So we're going to calculate the amount of heat transferred. Well, I'll give us the reaction first. Sorry, guys. So CH4, so methane plus 2 oxygen. So I have a combustion reaction again, producing carbon dioxide plus 2 water. And our enthalpy change for this is going to be a negative 890.3 kilojoules per mole. And our question is we're going to calculate how much heat is transferred when 20.0 grams of methane, which is CH4, is reacted. So how much heat is transferred when 20.0 grams of CH4 is reacted? So what I'm going to do is I'm going to convert my mass of methane to moles of methane, right? Once I have moles of methane, I can then multiply it by my enthalpy change. Moles will cancel, and that will tell me the total amount of heat that I'm transferring, right? Essentially, if we go back up to this, right, I have this number. We're going to get this number using our molar mass, and then if we multiply that, that will give me Q. Q is what we're solving for. So I'm going to start with my 20 grams of methane. I'm going to use the molar mass to convert it to moles. Since grams are on top, grams are going to go on the bottom. The molar mass of methane is 16.05 grams per mole. Right? There's 1 carbon and then there's 4 hydrogen. So if you calculate the molar mass, that's what you're going to get. So those are going to cancel. That's going to give me moles of methane. I'm just going to use my enthalpy change here. Since moles are on top, moles are going to go on the bottom. I have 890.3 kilojoules per mole. My moles cancel, and then that's going to give me the total amount of heat transferred. So I am grabbing my calculator here, if I can find it, and we will type that in. So 20 divided by 16.05 multiplied by 890.3, and that gives me 1,109.4. We'll do sig figs here in a second. Kilojoules of heat transfer. I do only want 3 significant digits, so this 9 is going to round that 0 up. So I'm going to have 1,110 kilojoules. Remember, if I don't have a decimal point, then this is not significant. So this number does only have 3 significant digits. You could write it in scientific notation also, but that would be the amount of heat that I'm transferring. I did drop that negative sign. If you're wondering why I did that, is the problem just wants to know how much heat is transferred. It didn't say is it being absorbed or released, it just says how much heat is transferred. Remember, that negative value only tells me that it's being released, right? It's being released. The amount of heat that's released is 890.3 kilojoules per mole, right? I'm not releasing a negative value of heat. The negative means it's releasing. My value, right, my amount of heat is 890.3 kilojoules per mole. So I did drop that sign, right? How much heat is transferred this much heat. If I said, which direction is it being transferred? That negative sign tells me it's being released. I'm giving it off, right? I'm losing heat energy. I'm giving heat energy to the surroundings. So do kind of be careful on the wording. Don't get tripped up by those signs again, right? The sign means direction, not magnitude. If my value for delta H is negative, again, remember anytime we see that negative sign in front of something, that delta in front of something, it's always final minus initial, right? So delta H is H final minus H initial. So if it's negative, that means my final is less than my initial, right? I lost heat energy. Remember, delta H is a measure of the heat of my reaction. So I'm still talking about heat energy here. So we lost heat energy, right? The system lost heat energy. We could add that if it helps. Means my surroundings gained heat energy. And then this is where our exothermic term would apply. So this is an exothermic reaction. If my value for delta H is positive, right, I have a positive enthalpy change. That means my final amount of enthalpy is greater than my initial. So my system, again, always from the point of view of our system, gained heat energy. Meaning my surroundings lost heat energy, and this would be an endothermic reaction. Again, heat is a form of energy, total energy is conserved, so if one is gaining, the other is losing, right? System lost heat energy, surroundings gained it. If you're holding on to a beaker that has an exothermic reaction in it, it's going to feel hot because you are in contact with the surroundings, right? Not the system. And an endothermic reaction, if you're holding on to a beaker that has an endothermic reaction in it, it's going to feel cold because, again, you're in contact with the surroundings, but our definition, right, is from the point of view of the system. Our system is gaining heat. Our surroundings lose heat. So again, for us, we're in contact with the surroundings. It's going to be the opposite. So an exothermic reaction is actually something that's losing heat. We're going to feel that heat that's being given off. An endothermic reaction is one that's gaining heat energy. Again, we're in contact with the surroundings, so it's going to feel like it's losing heat. It's going to feel like it's getting cooler. So is it a positive enthalpy change? If it is, it gained heat energy. Is it a negative enthalpy change? If it is, it lost heat energy. We could substitute my enthalpy change into my equation for total energy. So my total energy change is equal to work plus my enthalpy change. So instead of putting Q there, we could put our enthalpy change. And then I could ask similar questions to what I did in the first video, but using endothermic and exothermic. So kind of, for example, let's say it's an exothermic reaction. And let's say that our total energy change is going to be positive. I could say that it's absorbing heat energy. And then our question is, does the system or the surroundings do work? That's really hard to read. Does the system or the surroundings do work? So if it's exothermic, right, that means that I've lost heat energy. This is a negative value. It's telling me that my energy change is positive. I could have said if it's absorbed, then we know that it was positive. So then our question is, what does our sign on work have to be? So if my total energy change is positive and work is negative, delta H, my enthalpy change is negative, work has to be a positive value, right? If work was negative, a negative plus a negative would give me a negative, right? My energy change would be negative, but it's not, it's positive. So work needs to be a larger positive value than the negative enthalpy change. And if work is positive, who's doing the work, right? If it's positive, my system gains work energy. So what that means is my surroundings are doing the work. I kind of reasoned through it a little bit differently. So if that's not making sense, like the positive and gaining might make sense, but like who's doing the work, the system or the surroundings, that part could be a little confusing. It has been for me in the past. And the way I think about it is that if work is positive, right, if this is a positive value, that means that delta V has to be negative, right? A negative times a negative is giving me that positive. So that means my system is contracting, right? My volume change is negative, my system is contracting. And the way I think about it, if it's getting contracting, who's pushing, right? If my system was pushing out, it's doing the work and it would expand, right? It's getting bigger. If my system's contracting, what that means is that the surroundings are pushing on it, right? Something's making it get smaller. So because it's contracting, my surroundings are pushing on it, my surroundings are doing the work, right? If it's expanding, then it's pushing out on the surroundings, it's doing the work. So contracting, surroundings do the work, expanding, the system does the work. So kind of going through it again, it's exothermic. So this is a negative value. I just flat out told us what this was, which means this has to be positive. If work is positive, my system is contracting, which means my surroundings are the ones that are doing the work. Again, we don't always have work in chemical systems, right? If it's a constant volume, then my total energy change is due only to my enthalpy change.